Hello everyone, myself Ranjit. So I am here to explain my project, which is a steepest descent method. So first of all, steepest descent method is used to solve unconstrained optimization problems. So before starting, we need to know the difference between what is unconstrained optimization problem and constrained optimization problem. So if you take a constrained optimization problem, so we have one problem, whether it is maxima or minima. So we have a function of x, and they will give, or we have some subjected to another function. So which is one inequality basically. So g of x something less than or equal to some p. Okay, so this is nothing but constraint optimization problem. So the main thing here is that in constraint optimization problem, we have an inequality or one subjected to inequality function. So when it comes to unconstrained optimization problem, so here also we have a function. We have to maximize or minimize a function, but we don't have here subject to, to a inequality like here. Okay, so simply we have a function. We have to maximize or minimize the function. So there is no subject to inequality in unconstrained optimization problem. So these are the contents we're going to see in this video. So now, for solving linear programming problem, whether it's a constraint problem or unconstrained problem, so we know there are three methods, that is simplex method and become method and two-phase method. So basically begin method is the extension of two-phase method. And for solving non-linear programming problems, so we have Lagrange multiplier method, and for some conditions we have KKT method as well. So now, what is steepest descent method? So the steepest descent method, as I said, it is mainly used for unconstrained optimization problems, and it was a optimization algorithm used to find the minimum of a function. Suppose if in the question they given to find the maximum of a function, so simply convert into the minimum by taking the negative of the function. Okay, and basically these methods keep on updating the current solution. Means it iteratively updates the current solution by taking the steps proportional to the negative gradient of the function. So we have number of iterations in the search direction. So we keep on iterating until we get the optimization value, optimization solution. So before going to the details of steepest descent method, first of all, we need to know about what is monotonic function. So a function f of x is said to be monotonic if and only if function is either increasing or decreasing in its domain. Okay. So let's take example like this. Suppose this was the graph of a function, graphic something like this. So this was the graph of say some function f of x. Okay. So if you see, this was my origin, and let's say this point is some x1 and this point is some x2. Now if you see, from range 0 to x1, the function f of x is increasing, right? Okay. And if you see, after f of x to x2, the function is again decreasing, right? So this function f of x is not monotonic. Okay. So what I said, if a function is monotonic, is that function is either increasing or decreasing. So function should be strictly increasing in its domain or should be strictly decreasing in its domain. So let us take another example. Suppose if you see y is equals to x graph, so this was increasing, right? Increasing function. So in order to say the function is increasing, so if x1 is less than or equals to x2, my function f of x1 should be less than or equals to f of x2. Then we can say it is monotonically increasing. So this was the example for that. So this was my x1 and this was my x2. So if you see my x1 is less than x2. And if you take another example, that is y is equals to e power x, this is monotonically decreasing. So this is strictly decreasing, right? So for that, in order to be monotonically decreasing, my f of if x1 is less than x2, my f of x1 is greater than f of x2. You can see from this graph. Okay, so just keep in mind that if a function is strictly increasing or strictly decreasing in entire domain, then it's said to be a monotonic function. So suppose if you take this example, as I said, see, in this entire domain, the function is increasing and decreasing, and again is increasing. So this is not a monotonic function, basically. So next, we need to know about what is unimodal function as well. So a graph, the graph of a function has to have one minimum point or one maximum point only. Okay. Suppose if you take an example, y is equals to x squared. So this is unimodal function. So if you see the graph, this was the graph. So we have only one point, that is point of minimum. Okay. So if a graph contains only one point, the point can be either maximum or minimum. Okay. So then it's known as unimodal function. So suppose if you take a graph like this, something like this. So if you see this graph, it has this point is maximum point and this point is the minimum point. So this is not unimodal function. Okay, why? Because it has 2 points and 2 points, one point is maximum, one point is minimum. So in order to become a unimodal function, I have to have only one point. So one point either can be maximum or can be minimum. Like this case, y is equals to x squared case. Okay, so this graph is not a unimodal function. Okay, next. Suppose if you see this graph, so this was the function f of x, y is equals to f of x, and if you see this point is the local maximum, and this is local minimum. Okay, and if you see this point, this is known as the global minimum. So, what is the difference between local minima or global minimum? So the only difference is global minima is the minimum value of the entire domain or entire function, basically. But local minima is minimum to the some range of x. Okay, to take this x range from 0 to some value. So this the minimum value, the minimum value further. Okay, but if you take the entire domain, the minimum value is this one. Okay, that is known as the global minimum. So for unimodal function, the global minima and the local minima will be same or will be collide. Why? Because as I said, if you take this example, so this was the global minima and also the local minima. So why? Because as I said, for a unimodal function, we have only one point that can be at the maximum or minimum. So there is no global and local for unimodal functions. So there is only from minimum point or the maximum. So now let us see about the algorithm of a Steepest descent method. So as I said, this is known as an iterative method, and we can call it as gradient method as well. And suppose we have a minimization problem, we have to minimize some function of x. So for that, we have to start with an initial point. So let's say it was x1. So first of all, the step one is you have to start with the initial point x1 and iteratively move along the steepest descent direction until we get the optimal point. Okay, so we have to find the direction that is known as the search direction SI. So after finding the search direction, you have to move in that direction. So in order to find the search direction, we use this formula that is minus of gradient of f of x. So why we use the gradient here? Why? Because the gradient function, the gradient value gives the function like this, that it moves in a fastest rate. Okay, it gives the fastest rates at which the function moves. So basically, we use this. So why here negative sign? Negative sign says that we are minimizing the function of x. Okay. So next, in order to find the next point, that is x2, or we can say the second iteration point, we need to first of all determine the optimal step length, that is lambda I, in the direction of x. Okay. So listen properly. Suppose if you have initial point, so let's say that is x1. So we got the such direction like this. Let's say like this. So that is say s1. So by using this formula, that is si is equals to minus gradient of f of xi. So we got this direction. And at this point, we got our new point x2. Okay. Now the distance x1, x2, the distance between them is lambda 1. Okay. So this is nothing but the optimal step length. So from this, I can write my x2 as x2 minus x1 is equals to lambda 1 into s1. So from this, I can write x2 is equals to lambda 1 s1 plus x1. Okay. This was my next iteration, second iteration point. Suppose if you need the third iteration, so from this, again, we need to find the such direction, that is s2, and we get in another point, a third iteration point, that is x3, and the distance between optimal length is lambda 2. Okay, so I get my third iteration x3 is equals to lambda 2 s2 plus x2. So this is my third point, or the third iteration point. Okay, so next, after finding the new point x2, x3, or x4, we have to put it in the gradient value. And if you see that value, if it is equals to 0, then it was known as the optimal point. If not equals to 0, next you have to move to the side, next iteration. So that's the procedure. Okay. And now you will get a doubt that how to find the lambda I. So lambda I can be found using this formula. So lambda is equals to Si whole transpose into Si whole by Si transpose into H into Si. So if the example, minimize f of x1 comma x2, which is equals to x1 minus x2 plus 2x1 square plus 2 x1 x2 plus x2 square. So given the starting point is x1 is equals to 0 comma 0. So first of all, we need to find the gradient. Okay. So is equals to, so partial derivative of f with respect to x1, next with respect to x2. So if you do, I get 1 plus 4x1 plus 2x2. And if you do the function, the partial derivative with respect to x2, I get minus 1 plus 2x1 plus 2x2. Next, we need to find the Hessian matrix X. Why? Because we know the formula for lambda I, which is equals to Si transpose Si whole by Si transpose H into Si. Here H is nothing but Hessian matrix. Okay, so we need to find that as to get lambda value. So H is equals to, so formula is del square f by del x1 square, del square f by del x1, del x2, and del square f by del x2, del x1 to del square of pi del x2 square. So this is the formula. So this is 2 cross 2 matrix, right? Why? Because if there is x3, I get 3 cross 3. Okay. So this matrix is, so if you do the partial derivative, so this is the double partial derivative with respect to x1. So I get 4, 2, 2, 2. So this is my Hessian matrix. So now I need to find x2. So that is iteration 1. So iteration 1, I need to find x2. So x2 is equals to x1 plus lambda 1 into S1. So I know S1 is equals to negative of the gradient. So that is del of f of x1. So which is equals to, so if you substitute x1, that is x1 which is 0 comma 0. So if you substitute x1 comma x2 0 comma 0, I get here del of f of x1. Okay. So I get minus 1 and 1. So next I need to find lambda 1. So which is equals to S1 transpose S1 whole by S1 transpose H into S1. So this was the matrix, right? So S1 transpose is minus 1, 1 and 1, 1 whole by minus 1, 1. Asian matrix is 4, 2, 2, 2 into S1 which is 1, 1. So if we simplify this matrix and divide it, I get as 1. So from this I can find my x2. So x2 is equals to, so x1 is the starting point, that is 0 comma 0 the given, plus 1 into minus 1 1. So I get it as minus 1 1. So this was my x2 point. So check whether this x2 is my optimum solution or not. So in order to check it was optimal or not, so I have to find out the gradient of f of x2. So I will get as minus 1 and minus 1. So this is not close to 0. So this my x2 is not optimum. Okay, so I need to go to the next iteration. So next iteration is nothing but finding x3. So next iteration, that is iteration number 2. So I need to find x3. So x3 is equals to x2 plus lambda 2 into s2. So first of all, I need to find S2. So S2 is equals to negative of gradient of f of x2. So I will get it as 1 comma 1. Okay. So I need to find lambda 2. So lambda 2 is equals to S2 transpose S2 whole by S2 transpose H into S2. So I'll get it as 1 by 5. So from this I can find x3, which is equals to x2. So x2 is the previous point, that is the minus 1 and minus 1 plus 1 by 5 into 1, 1. So I'll get it as minus 0.8 and 1.2. Okay. So next we need to check whether this x3 is optimal or not. So for that I need to find gradient of f of x3. So which is equals to, I will get it as minus 0.2 and minus 0.2. So this is not close to 0. So therefore my x3 is not optimal. Okay. So I need to find x4, that is next iteration, that is iteration number 3. So next I'm going to do third iteration. So for that I need to find x4 value. So x4 is equals to x3 plus lambda 3 into s3. So s3 is nothing but negative of gradient of f of x3. So I will get it as minus 0.2 and 0.2. So next I need to find lambda 2, which is equals to S3 transpose S3 whole by S3 transpose H into S3. So if you find out that, I will get as 1. So from that I can find max 4 point, which is equals to minus 0.8 into, and next is 1.2 plus 1 into minus 0.2 and 0.2. So which is equals to minus 1.0 and 1.4. Fine. Next, we have to check whether this x4 is optimal or not. For that, I have to do gradient of f of x4. So, which is equals to minus 0.2 and minus 0.2. So, this was not equals to 0 comma 0. So, therefore, my x4 is not optimum. So, next we have to move to the next iteration, that is iteration number 4. At iteration number 4, we have to find x5 point. So next we are moving to the next iteration number 4. So now we are going to find out x5 point, which is equals to x4 plus lambda 4 into s4. So s4 is equals to minus negative gradient of f of x4, so which is equals to 0.2 and 0.2. So next we need to find lambda 4, so which is equals to S4 transpose S4 whole by S4 transpose H into S4. So which is equals to get as 1 by 5, and we need to find X5. So X5 is equals to, so X4, that is minus 1 and 1.4 plus 1 by 5 into 0.2 and 0.2. Okay, so if you simplify this, I get minus 0.96 and 1.44. So next we need to check this x5 is optimal or not. For that I need to do gradient of f of x5. So which is equals to 0.04 and minus 0.04. So which is pretty close to 0, right? So I can say my x5 is optimal. Why? Because it's close to 0. So now let us see the MATLAB example for that question. So here is the MATLAB code. So first of all, let us define the function. So next we have done the inline. So in order to get the value corresponding to the x1, x2 values. Next we have defined the gradient of that. So to find s1, s2. Next we have to define the xn matrix in order to find the lambda values. So this was the main code of the steepest method. So here we have done all the calculations, all the substitutions to find the iteration points, that is x1, x2, x2. So for that we have used while loop. So while loop generally is nothing but iteration loop. So while loop helps us to find the points x1, x2, x3. And last we have to print that solutions, right? So for that we have to use printf. So this was the optimal solution for that question. So optimal value. So we got it as minus 1.249. So optimal solution is this one. Okay. Thank you.